Hey, good morning. Welcome back to physics. I am Mr. Branca. I'm going to kind of go over our first lesson here today, or wherever you're going to be taking notes. Ready? Go over a few new things. Okay, this is going to be graphing motion in AP Physics 1. I put on here for the first slide a couple of reminders. The first one, make sure that you are logging into Canvas each day for each of your classes and that you are completing the assignment for those classes so you can get your attendance credit for that day. I will also be sending out notifications on Remind. Please make sure that your phone is set up to receive those notifications. And then third, I will be having office hours on Friday. If you have any questions, please come by. The links for that is in Canvas in the About Your Teacher section. Okay, learning objective and guiding question for today. Learning objective, I can construct and interpret graphs of a position, velocity, and acceleration versus time graph by using the slope and areas under the curve of a motion graph. The guiding question then is, how can I construct and interpret a graphs of a position, velocity, and acceleration versus time graph? Today is going to be the introduction to those topics. We'll just go through what those will look like. All right, motion definitions. I always like to start with definitions and formulas that you're going to need for this section. The first two are going to sound very similar. I'll give you examples so you can understand the difference between the two. Distance is the total length of a trip. So the entire length from wherever you went to wherever you got back to. Displacement is simply how far you are from where you started. So here's a very quick example that'll help it make sense. Let's say you drive from your house to the grocery store to Chick-fil-A and then back home. That whole trip may have been like 10 miles to go do all of those things. So the distance for the trip would be 10 miles. But the displacement is how far you are from where you started. Well, if you started at your house and you finished at your house, your displacement would be 0. So that's the difference between distance and displacement. Then the next two, speed and velocity. So speed is distance divided by a time. And then velocity is displacement divided by time. You'll see in the front of each of those, there's a little triangle. That just means the change in distance or the change in displacement. One of the key things in velocity is velocity also includes a direction. So if you are moving up or down, that's usually considered to be negative. If you're moving up or to the right, it's considered to be positive. The next definition we're going to go over is acceleration. Acceleration is the change in velocity divided by time. You'll notice it still has that little delta, little triangle there in front. That just means change. And then acceleration also includes a direction. And then the final two definitions, scalar values contain a number but no directions. So distance, speed, mass, none of those have a direction to them. Vector values are numbers that also have a direction with them. So an example for that would be displacement, velocity, acceleration. So here's a way to kind of tell those apart. So if you're driving your car and you look down and it says, I'm going 30 miles an hour, that would be a speed. And it'd also be a scalar value because it doesn't have a direction to it. Say you're looking into your car and it says, I'm going 30 miles an hour, and sometimes it'll have a little north, south, east, west. Well, if you combine the 30 miles an hour and south, that would be a speed and a direction, which would give you velocity, and that would be a vector because it gives you both a number and a direction. Okay, I like using these little diagrams because it helps to see where things are going and how they're moving. Okay, so if we look at this one, you've got a little car, and what I want you to think about is this car has a little oil leak to it, and it's dropping that oil every second. So just every second it's dropping one drop of oil. So what you see on here is the drops are evenly spaced out as the car is traveling. On the bottom one, I just put the drops of oil and just took out the car. So by examining the oil drops, you can draw some conclusions about the object's motion. What is it doing? So what I want you to look at this for a second is, what do you think the car is doing? If you need to pause the video here, that'd be a great opportunity. And just jot down, what do you think the car is doing based on those drops that you see? So hit pause, write down what you think it is doing, and come back. Okay, hopefully you've paused it and didn't just keep going. So what you should kind of conclude from the drops, if you see these, is this car is moving to the right when you see the car, and it was probably moving at the same speed the entire time because the drops are evenly spaced out. What we can't tell from this bottom drawing is the direction. We see that there are drops there, but we don't know, was the car actually moving to the right or was it moving to the left? We don't know that based on the drops. Once you add the automobile in there, you probably can tell. All right, so this next one is another particle diagram, and it's going to help us see what it would look like if an object was accelerating. Simply, was it getting faster? So you'll notice the drops are initially really close together, then they get a little further apart, and then they get a little further apart, then they get a little further apart, further apart, further apart, further apart. So what you could conclude from this is the object was accelerating to the right and speeding up. Now here's another question for you, just to kind of pause the video, think about it, and jot down what you think. Can you think of a case where the car could have a negative velocity? So negative would mean the car was moving to the left, and have a negative acceleration, yet speed up. So take a minute there, just kind of pause it, and write down, okay, how could it have a negative velocity and a negative acceleration? So how could it have a negative velocity and a negative acceleration? So pause the video there, see what you think, and then we will come back here in just a second. We're going to be back looking at this dot diagram with the car. So one option on this is it started slowly and was accelerating to the right, getting faster and faster. Another option it could have is it was initially going to the left, so that would be a negative velocity, and it slowed down. So it could be headed to the left and it was slowing down, or it could have been going to the right and it was speeding up. So those would be our kind of two cases with this dot diagram. Now this question I asked you to think about when you're pausing the video, can you think of a case where the car could have a negative velocity, which means it would be headed to the left, and a negative acceleration, yet speed up? So here's what that could look like. You would need, because all the negatives tells you is a direction. So negative direction, negative velocity means it's headed to the left. Negative acceleration would mean it's also accelerating to the left. So what that would look like is they're traveling to the left, and instead of pressing their brake, they're pressing the gas. So that's a way that you could have a negative velocity and a negative acceleration. Okay, we're going to look at our position versus time graphs. These are our first types of graphs that we're going to see and kind of deal with. Just go over what they mean and go through how to interpret one of them. Okay, so what I want you to picture this is a dog and he's out walking. So the dog starts at the 1 meter mark. So our initial time would be 0, and he's starting at 1 meter. Then the dog walks away from his owner at a constant velocity of 0.5 meters per second. So here's what he does. He starts at this 1 meter mark, and he walks up to 3 meters away. So he's just walking he walks 2 meters. He walks from 1 meter to 3 meters. So he covers a total of 2 meters, and it takes him 4 seconds to do that. If we wanted to figure out his velocity, we would take 2 meters, divide it by 4 seconds, and his velocity would be 0.5 meters per second. The next section we're going to look at is from 4 seconds to 6 seconds. We want to look at what is going on there. So the dog, when he gets to 4 seconds, you'll notice for this time interval, he's just staying at 3 meters. So he's not moving, he's not moving, he's not moving, he's not moving. So he is simply just stopped. So his velocity is going to be 0 meters per second. Then right below it, the dog on the next part, he walks backwards. He's walking back towards where his owner was. So he's at 3 meters. He walks back. He's walking back as time goes by. And down here, right when he gets 1 meter, that would be where he's even with his owner again. And then he doesn't come right back to him. He just goes back past his owner. Now, if we wanted to figure out his velocity, we would figure out he traveled from 3 meters to 0 meters in 3 seconds, and that would be a negative 1 meter per second, and that would be his velocity. And the negative is because he was traveling backwards. So we're going to go over that a little bit more here on the next slide. So keys of a distance versus. Hey, welcome back to part 2 of our distance versus time graphs. Okay, we were talking about the keys of a distance versus time graph. So the biggest key is this very first bullet point. The slope of the distance versus time graph will give you the velocity. So slope is simply the rise over run. Anytime, just like what you have done in your math class to get slope. So if we look at each section of this, slope of the first part of the graph, our rise would be he goes from 1 meter to 3 meters. So that would be 2 meters distance. And then how long did it take him? Well, how much time went by? He was at 0 seconds to 4 seconds. So that's a total of 4 seconds. So 2 meters divided by 4 seconds gives us 0.5 meters per second. On the second part, it has a flat horizontal line. And if you remember from geometry, if you have a flat horizontal line, the slope of that line is 0. So the dog for that portion has a 0 velocity. Then if we look at this last part, one thing we can tell that's different from the first section is it has a negative slope because it's headed downwards. Then if we're looking at how far down does it go? Well, it goes 3 meters because it goes from 3 meters down to 0. And then how much time goes by? It goes from 6 seconds to 9 seconds. So that's a total of 3 seconds. Negative 3 meters divided by 3 seconds gives us a negative 1 meter per second. So that's how to look through a distance versus time graph. Our next part is looking at a velocity versus time graph. And I took that same graph we were looking at last time. So this is a distance versus time graph up at the top. And I made it into a velocity versus time graph. Now here's how to do that. A velocity versus time graph shows the velocity as a function of time. Here's how it's related. It's related to a position versus time graph by the slope. So if you remember from what we talked about from the previous slide, is the slope of this line, the slope of this line, and the slope of this line were the velocities for those sections. So we said the velocity for this first line was 0.5 meters per second. So all I did was I graphed the line at 0.5 meters per second for the first 4 seconds. And I did that in a little black line. For the next section, from 4 to 6 seconds, it didn't have any velocity. So I just put the line down at 0 because that was the slope off of my distance graph. And then for my last one, from 6 seconds to 9 seconds, it had a slope of -1. So here's my line representing -1. So that is how to create a velocity versus time graph from a distance versus time graph. And you're simply taking the slopes from these 3 lines and going, the slope of this is my first part, and the slope was 0.5. My slope of the second part was 0. So I just graphed that straight line at 0. And then my slope for the last line there was -1. So I graphed that at -1. So now we're going to look at a velocity versus time graph. And what does that tell us? The slope of a velocity versus time graph is equal to acceleration. The area under the curve is what's called displacement. So what we're going to look at is, what is the acceleration of the car? We're going to answer 2 questions. What is the acceleration of the car at 0.5 seconds? So what we would need to do for this section is take its slope. So we would go, if I go for this entire line, it goes from 0 to 10. So that would be my rise would be 10. And how long did that take to happen? It took 4 seconds. So 10 divided by 4 would give us 2.5 seconds. Go back real quick. So that would be the acceleration of that car, would be 2.5 seconds. Then what is the total distance traveled by the car during this 6-second interval? So here's what we want to do for this. We want to do what's called the area under the curve. So we're going to treat this line, the x-intercept 0, as basically our bottom to this. And we're going to divide this into a triangle and into a rectangle, and we're going to take the areas of both of those sections. So for this triangle section, we're going to get the base of it, which would be 4. We're going to get the height of it, which would be 10. And if we did 4 times 10, that should give us 40. But since it's a triangle, we have to cut that in half. So half of 40 would be 20. And then we're going to do the area for this second part, this rectangle area here. So this section. So the height of it would be 10 again, and the amount of time would be 2. So 10 times 2 is 20. So we know the area of this triangle section was 20. The area of the rectangle section was 20. To add it together and get the total distance, it would just be 20 plus 20, which would give us a total of 40 meters. And then this part, an acceleration versus time graph. Taking the slope of a velocity versus time graph will give you acceleration. And then taking the area of the acceleration versus time graph gives you the object's change in velocity. So down here, I put this little thing together just to kind of give you some ideas of how to work through these. So if you have a distance versus time graph and we want to move to the right, we're going to get the slope of it, and that'll give us our velocity. And you'll notice this distance versus time graph is curved, which means our velocity is changing. And then if we go to the next one, if we take the slope of the velocity versus time graph, that will give us our acceleration line. And if we work backwards, if we go the other direction, the area of our acceleration versus time graph will give us our velocity versus time. And then if we work backwards off of this and get the area of our velocity versus time, it will give us our graph for distance versus time. All right, practice question. So I want you to take a minute with this, just kind of look through it. Which graph represents the motion of a block accelerating uniformly down a ramp? So I want you to pause, look at these 4 graphs, and decide which graph, 1, 2, 3, or 4. So 1's on top, 2, 3's on top, and then 4. Which graph do you think best represents a block accelerating down the ramp? So pause, and we'll come back and talk about it. All right, good, you pause it. Now we're gonna go through it. So distance, our number 1 graph, distance, what that one's showing us is it's just staying at the same exact location. It's not changing, it's just staying in one spot. So that one is not accelerating because it's not even moving. Our graph down number 2 is the distance is changing over the same interval. So we've got a nice straight line, which means we have a constant velocity. So that one's not accelerating down a ramp, it's just moving at a constant velocity. The graph number 3, it's got a constant velocity for the first part and then stops on the second part. And then our very last graph down at the bottom, this is the one that's accelerating. So if you see a distance versus time graph that's curved, that's going to be your big hint that it's accelerating. All right, here is your exit ticket for today. You'll see this in Canvas. Go to, and I'll have this posted on there. You'll go to this link. It's got some practice things that you can do with graphs and tracks. It'll have some tracks and a ball that you can use and see how that works. And what I want you to do is look at the tutorial section. You can adjust the hills, and what you want to try to do is make the ball's motion match what's going on in the graph. So spend about 10 or 15 minutes with that. Once you've done this, there will be a little exit ticket at the end, and you will be done for the day. If you have any questions, please feel free to come by in office hours. All right, you guys have a good weekend. Thanks. Bye.